In this video, we're going to investigate orthogonal and parallel vectors by way of an example. So we're asked to determine whether the given vectors are orthogonal, parallel, or neither. So in part A here, we've got u is the vector -3, 9, 6, and v is the vector 4, -8, 4, -12, -8. Well, checking whether or not two vectors are orthogonal is a pretty straightforward process. Remember, with the dot product, we can check to see if two vectors are orthogonal. They will be orthogonal if and only if the dot product turns out to be 0. When we do the dot product, we take the product of the first components, product of the second components, product of the third components, and add them all together. In this case, you do that, you'll get -168, which is certainly not 0, so these vectors are not orthogonal. Parallel, however, is a matter of checking to see whether or not one vector is, if the vectors are constant multiples of each other. In this case, notice that in order to get 4 for v, I would need to multiply in the x component for v, or the I component for v, whichever way you want to think about it. I would need to multiply the I component of u by -4/3 to get 4. That same number, -4/3, works for 9 and for 6. -4/3 times 9 gives me -12. -4/3 times 6 gives me -8. So in that case, we see that v is a constant times u. So therefore, the two vectors are parallel to each other. For part B, we're given two vectors. We're just given to them in the ijk component form rather than writing them as components themselves. So again, checking whether or not they're orthogonal, we do the dot product. 1 times 2, -1 times -1, 2 times 1, add it together, you get 5. 5 is not 0, so the vectors are not orthogonal. Now do the same process like we did for part A to check whether or not they're parallel. In order to get 2i from I would have to multiply u by 2 to get that first component to match up. However, if I multiply -j by the same constant, that 2, I get a -2j. I don't get -j. So I do not get the j component of v. So in particular, v is not a constant multiple of u, and vice versa. Therefore, they're not parallel. So in this case, they're neither orthogonal nor parallel. Finally, let's look at an example here that just has some unnamed constants in the components here. This case, again, checking whether or not they're orthogonal. We can do that through the dot product. A times -b plus b times a plus c times 0. We really do get 0 in this case. So no matter what a, b, and c are, these vectors will be orthogonal to one another. Let's see if they're also parallel. Now, it may not seem to make sense, but technically, if they're the same vector, they can be parallel to each other. A vector is parallel to itself. So, and that's actually what we would get to in this case. All right, so to run through this to see whether or not they can possibly be parallel as well, let's suppose we have a non-zero component here for a, for this first component. I would have to multiply it by -b over a to get the -b for the v part. However, if I multiply that by the b, I do not get a in the second component for v, because I get -b squared over a, which is not a. Okay. So if a is not equal to 0, then they're not parallel. If a is 0, then notice I would have a 0 here in my second component. I'd have a b times something to give me 0, and then 0 times something to give me -b. I would need b also to be 0. Okay, so that's the only way we can possibly get it, and then z would also have to be 0 in that case to get them to be parallel. So the only way they're going to be parallel in this case is if all three constants are 0. So they're parallel to each other if and only if they are both the 0 vector, which isn't very interesting, but we do have a case where they're actually parallel to each other.